So what do we have here? In the applet, we've got two graphs. One graph on the right is a dx dt versus x graph. The other one is an x versus t. Now, to be really clear about the different axes, what we have, actually, let's do just typing. We have the dx dt, and I'm typing, it'll display, I think, in a second, the dx dt axis. And then we have the, let me put this in green, the x-axis. Then over here, we've got also the x-axis. And then finally, let's say the t-axis. So note that we have dx dt, which is right here. Then we have the x-axis, which is along here. It's the exact same x-axis over here on the right. And then we have the t-axis. This all stems from currently the function that is dx dt is equal to x minus 3, which I'm highlighting down here, times x plus 3 times x divided by 4. If you were to just simply forget about all the differential equations, slope field stuff, and you were to just take the polynomial x minus 3 times x plus 3 times x divided by 4, and let's say you set that equal to y and then graphed it on a y versus x axis, you would get something like we see here. You get exactly this, in fact. So you have this cubic polynomial graph. At the same time, we're saying let dx dt be equal to this. So based on what we looked at last time, what that means is dx dt is a slope. So when you look at an x versus t graph, you have dx, change in x, over dt, change in t. So that gives you a slope. For instance, when we have, let's say, x is equal to, I don't know, 0, for instance, we have x minus 3, x is 0, so we have negative 3, 0 plus 3, which is 3, and then we have times 0, so we get slope of 0. Now, we're talking about autonomous equations here. So when we look at these equations, we'll have the formula only depend on x. Notice there's no t in here. I think even if you try to enter a t in here, it either won't accept and give error, or it will just sort of ignore it. So when we're looking at these functions, since they're autonomous, it only depends on x. And maybe just to be really clear, when we're talking about autonomous diffeqs, if we're working with these particular variables, that's something of the form dx dt is equal to just some function of x. Notice there's no t there. F only depends on x. So we have these two graphs. They both come from this function here, this dx dt, blah, 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 blah. And we can change the functions and get different graphs. Like if you graph cosine of x, you know that's an oscillating function. So here's cosine of x, like we're used to seeing. And then here's the slope field like we saw last time. So we're taking just regular function graphing like we've done a lot in mathematics for quite a while. Then we are looking at how that compares to slope fields here. So just graphing the functions on the left and then slope fields on the right. All right. So now let's get into it. So like I said, I'm going to kind of just type on the screen what we're trying to do, going through the lab instructions so that we can keep the applet up the whole time. So let me first clear this. And now I'm going to actually reset back to, actually, let's do this one. Let's do x minus 3 times x plus 1. What we're going to do is we're going to go through a, I guess, 4-step process. The first process is we're going to look at functions, and I'll mention which functions. At those functions, we want to determine where the function is positive, negative, and 0. That's the first thing we're going to do. We're going to then, after that, conjecture how the function informs the slope field. Then we're going to test our conjecture, or I should really say conjectures, because everyone will make a different one. or at least superficially different. And then we're going to move on or make a new conjecture. That's the 4-step process we'll follow for the first part of this lab. And then we'll do something pretty similar for the second part of the lab. So right now we're going to focus on just the first part here. So we're going to look at different functions. Those functions are going to be the following. dx dt is equal to, one of them is what I've already put here, x minus 3 times x plus 1. We're then going to want to look at dx dt is equal to x squared minus 4. And then we're going to want to look at dx dt is equal to x squared plus 1. So we want to look at these functions. It's from these functions that will make our conjecture. So if we look at, let's say, dx dt is equal to x minus 3x plus 1, that's the function I have here. X minus 3 times x plus 1, that's a quadratic polynomial. So x squared plus yada yada. All quadratic polynomials are parabolas. Since it's x times x, and that's positive, we'll have an upward facing parabola. And now what we want to do is just look at this function, and really simply, it's nothing complicated here. We're just going to say, where's the function positive, negative, and 0? Well, clearly, there's a spot here where it's 0, and there's a spot here where it's 0. So the places where it's 0, there's 2 spots. And you can kind of see the relationship between the two, which don't worry too much about at the moment. That'll be more important when we make the conjecture, but you can see how it aligns with the left graph and the right graph. So like I was saying, there's this function, this parabola, it's 0 at 2 spots. Now, if we look at where it's negative everywhere in here. The red line even stresses that it has to go down to meet the curve. So everywhere in here, it's negative. We would then say it's negative on this interval, which I'll type here. So it's negative on interval. And the interval, I think those are hash marks are units of 1. So it'll be the interval -1 up to 3. I wanted to space it out a little bit. It looks like this. Then you would say it's positive on intervals, which I won't say explicitly, but I'm sure you'll be able to figure out. It's positive, let's say, over here on an interval, over here on an interval, and so on. So you want to do that for each of these 3 functions. I'll give you, let's say, a minute or two to run through these functions and just do that really quick. So we're currently doing part 1, and feel free to private chat me if you have specific questions, you're not quite sure. I'm happy to answer, or if you want to double check something that you come up with. And someone asked a question for the places where it's 0. Yeah, for these, they'll each, like for this function, it'll just be 0 at like discrete points. So you just put, let's say, x is equal to -1, x is equal to 3. If it's 0 for a bunch of points in a row, then you could put in an interval, but that it'll just be discrete points here. So you can say x equals whatever. Okay, at this point, you've looked at some different functions. You've decided where those functions are going to be 0, negative, and positive. Now, what we'd like to do is then go ahead and see if we can establish a relationship between the functions on the left, specifically where they're 0, negative, or positive, and then the slope fields on the right. And when I say how the function informs the slope field, what I mean by that is we would like to say that looking at the function on the left, can that tell us something about the slope field on the right? The answer to that is resoundingly yes, it can. And specifically, we'd like to conjecture how it does that. And I have to be careful here, because if I explain too much, I'll just say exactly what the conjecture is that you want to come up with, and then you don't have the opportunity to sort of make that connection. And if you're able to make that connection, it's better than me doing it, since it'll stick in your mind more, and it'll also just be more satisfying, I think. So let me try to explain this well enough so that you're able to make the conjecture, but I don't just give it away. If we look over here on this particular function, we'll notice that when the function is 0 here, and we look at the slopes, something in particular happens. Again, when we're over here and the function is 0, something in particular happens with the slopes on the right. That may or may not be clear. If it is, you probably see where I'm going next, but if not, something in particular happens when the function is 0. And when I say something in particular, I mean the slopes look like a particular thing. Then when we look at the function and it's negative, the whole while that function is negative, something happens. Meanwhile, whenever we look and we see that the function is positive, we could say that something happens. And that's true here as well as here. So what you want to do is say that when the function is 0, blah, blah, blah. I mean, don't literally write blah, 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 but like whatever you think happens on the right in the slope field. You'd say when the function is 0, such and such happens in the slope field. When the function is negative, such and such happens in the slope field. When the function is positive, such and such happens in the slope field. So that's the conjecture you want to make now. So I'll give you, let's say, a minute-ish to come up with your own conjecture, and then we'll go from there. And if you want to check your conjecture with me, feel free to private chat it, and I'll take a look at it and let you know what I think. So right now we're on step 2. Okay. I've received a few conjectures and given responses. They're looking good so far. Actually, someone just also sent me a conjecture that looks good. So if I haven't responded to you so far, all the conjectures I've seen, look good. Now, let's say I make the following conjecture, which is not going to be a good one, but I just want to show you what happens when a conjecture is, let's say, not so great. Now, this is something you want to do even if I have said that your conjecture looks good, just for sort of peace of mind, or if you didn't have someone who could check your conjecture and see whether it's true or not, this would be something you would do on your own. So let's say I make the following conjecture. I conjecture that when the function, when f of x is equal to 0, the slope field, the slopes in the slope field at the corresponding x values, at the corresponding x value are, let's say, are positive. Say I make this conjecture. There's actually a few problems with it. But for starters, what I might do is I just might want to test it. So I'm going to come up with, let's say, some new function, say cosine of x. I'll update the graph, and now I'll look and see when this function is equal to 0, which is, let's say, about here, or about there-ish. And now I test my conjecture. So I look and see, here's a spot where f of x is equal to 0 at this about 1.55, which is pi over 2. And then I look at the slopes over here, and I see that they're not positive. They're 0. So this conjecture is false. I've made a statement in this conjecture that is not true. If you've done that in your conjecture, what you want to do is go back then and make a new conjecture, one that hopefully is more in line with what actually happens here. And then, again, get back to this process, this point in this sort of process where you test the conjecture. So this conjecture I made is purposely bad. It's purposely, false. It doesn't align here. That means there's an issue there. There needs to be revision. Moreover, there's also an issue of being complete. Like there are other cases that this conjecture does not cover. So there are a few different revisions. Revision 1, a claim is made that is false. So that's one problem. A second problem is it's incomplete, so to speak. And when I say that, what about the other cases where f of x is greater than 0 and f of x is less than 0? So this conjecture would need two revisions. So you can check your own conjecture and see, are you making a claim that's false in the conjecture? Or is it a complete conjecture? And then address those correspondingly. So that would be the process of testing and then revising the conjecture. So you would test. I tested this conjecture that ended up making a false claim. But then let's say I go through the process, I do some revisions. Eventually I get to a place where I'm satisfied with the conjecture. During that process, I end up with a good conjecture, then we would be done. So you'll have to sort of look through that on your own, though you're welcome to double check with me your conjecture if you like, but that's largely just a thing to go through based on your individual conjecture. Now with that, what I'd like to do is to move on to the second part of this lab. It'll follow the same format where we'll look at some behavior, like step 1 here. We'll then make a conjecture based off of the behavior we observe. We'll test our conjectures. And then finally, we'll either revise our conjectures or we'll move on. So those are the 4 steps that we'll go through again in the second part. But now we're going to look at a new, I guess, set of behavior, types of behavior. So let me go ahead and clear this screen. And now I'm going to actually reset back to the function that we had started with, because I think it's a good one. X minus 3, x plus 3 times x divided by 4. I'll update the graphs. And now let me remind myself. Right, okay. So here we're going to be looking at equilibrium solutions. So let's talk about what that is. Let me get text ready and we'll do equilibrium solutions. And I don't want it to be quite that big. Here we go. So an equilibrium solution is a solution that looks like this. X is equal to x. Yeah, I can't typeset it very well, so I'll just have to do underscore 0, which of course means sub-0. So we have x is equal to x sub-0 or x naught, where we're going to say that x0 is a fixed real number. And that's important. So in other words, x is a constant function. Let's see. Wait, did I want to say more? Equilibrium solution. Yeah, I should say a little bit more. So it's this. And as a note, where x is a solution. Actually, maybe I'll just have it be implied. So there's 2 things. There's the equilibrium part is something you would talk about when you're talking about autonomous equations. Notice that this is really just a singular solution because it's a constant solution. It's called equilibrium because of the context of looking at an autonomous equation. So that's where equilibrium makes sense. Saying equilibrium solution wouldn't make sense out of this context. And then calling it a solution means it's a solution to this differential equation. Now, if you take the differential equation, dx over dt is equal to, actually, let's say it this way. Dx naught over dt is equal to x naught minus 3. So what I'm doing is I'm taking the equation we have above, and I'm substituting every instance of x with x naught. So that's it. Every place you see x, I'm putting an x naught. Suppose we do this. Now, just to double check that you're sort of with me on this, if x naught is just some fixed real number, can you just say in private chat, and whether you're right or wrong, I'm not worried about it. I'm just kind of seeing where you're at, if you're following along, if I'm going too fast or whatever. If x naught is a fixed real number and you take ddt of that real number, if you take the derivative of a fixed real number, what are you going to get? What should I put under here? Just whatever you think. If you're not sure, just put something. I just want to know where you're at, make sure I'm making sense. So taking the derivative of a fixed real number, which is x naught, what should that be? For those of you who put something in chat so far, thank you very much. All right, that looks like a good chunk of people, if not everyone. All right, looks good. In fact, it is 0. So excellent. So when we take the derivative of a constant function, just like with the singular solutions, we get 0. Now over here, we're going to get everything we had. I'll just try to type that real quick. Okay, good. Now what that means is we're just trying to find out where on this function we have 0. Because this right-hand side is the function with now x naught substituted in. So what are the roots of this function? Where do we get 0? We get it here. It looks like -3. Well, it is -3. We get it at 0, and then we get it at +3. Now you'll notice, and this is something to think about if you weren't sure from your conjecture, we'll notice that, oh, the slopes there happen to look a certain way. And if you follow the solution curves at those slopes, let's say here, if you follow that through, what you get, and I'm going to put this in, I don't want to do just red because we'll add that in a bit. What would be a good equilibrium solution that stands out? Let's do green maybe. And I'm going to draw this like so. I'm going to try to draw it straight, but I'm using a mouse, and drawing straight with a mouse is essentially impossible. Actually, let's not use green because that's that axis. Let's use magenta. So here is an equilibrium solution. Down here is also an equilibrium solution. And then finally down here, and I'm sorry I haven't figured out if there is a tool how to draw just like nice, perfectly straight lines in Zoom yet, but here are 3 different equilibrium solutions. Now, if we go ahead and we plot different integral curves, something interesting will happen. So I plot a bunch, and actually, yeah, I'm reminded here. Let's stress this more by doing this. So notice I haven't changed the equilibrium solutions. There we go. That's a little nicer to see, I think. Now, interesting things happen around the equilibrium solutions. Up top, we have a case where the other solution curves that are near it, or at least start near it, they get pushed away. So notice here, you start near x is equal to 3. I'm not sure what it is exactly. Maybe it's like x of -4 is equal to 3.25 or something like this. And it gets pushed away. And if it's below it, it gets pushed away. When we look at the equilibrium solution in the middle, all the solution curves get pulled in toward that solution. And then with the equilibrium solution on the bottom, again, we see the solution curves get pushed away from it. In cases where the solution curves are pushed away, we call that an unstable equilibrium. Basically, if you just perturb yourself slightly off of that equilibrium, off of that line, all of a sudden now you're going to never return to the line. You're going to get pushed away. And correspondingly, so let me just maybe say that real quick. So we've got here an unstable equilibrium. And it's the same down here. We also have an unstable equilibrium because the solution curves get pushed away. On the other hand, we have what we call stable solution or stable equilibrium in the middle. Oops. Let's do this one. Stable equilibrium. And we'll maybe color that blue. So in some sense, and let me try to draw this. For unstable, the solution curves get pushed away, solution curves that are near it. For stable, they get pulled in, and then unstable is again the same thing. They get pushed away. There's one other type, or maybe two types, but we use the same name, and that is something called the semistable. And I'm curious if you would just take a guess in chat what you think that is, and I'll sort of highlight it. If unstable pushes away both directions, if stable pulls in both directions, what do you guess semistable would do? So if you would just say in private chat what you think, what could another possibility be than what we have for unstable? Okay, I'm seeing some good responses here. Okay, yeah, a lot of good responses. For those of you who put something in chat, thank you. This is good stuff. Yeah, in fact, you'll get one of two cases. In general, what you'd say, like a lot of you have said, it'll pull in from one side and push out from the other side. And you can have one of the two, either one. Let's say I want to draw. So one thing you could have would be, let's say it pulls in from above and then it sort of pushes away from below. Or you could have reverse. You could have it pushes away from above and then it pulls in from below. Either one of those would equate to semistable. All right, good. Here we have just unstable and stable. I'm not sure about this class. In previous classes, we've called semistable also unstable. I'm not 100% sure offhand. It might say in the report, but I don't want to take the time to really look it up because it's not really important at the moment. But just to be aware of those. Now, what we'd like to do here, let's see, should I clear all this? No, not quite yet. I won't clear it yet. If we look over on the graph here, we'll notice that when we look at, let's say, this point, -3, we get this unstable equilibrium. Then looking at the graph on the left, so focusing on the graph on the left over here, when we're at x is equal to 0, we get a stable equilibrium. And then here we get unstable. So in some sense, it seems like it might be possible to look over here and just say, this is going to be unstable. This will also be unstable. And then here in the middle, we might say that's stable. But the question is, how do we do that if we don't necessarily have the graph on the right? That's sort of the question. If you had to block out the graph on the right and just look at the graph on the left, how could you tell, without seeing what the slopes actually are, how could you tell if it's unstable, stable, or stable just by looking at this graph on the left? So for instance, I'm going to clear all this. And then I'm going to write a function, but I won't actually graph it because then you could just see what the curves are. I'm just going to write a function, and I'm curious. We'll just take a go at it. dx dt. Let's set that equal to x squared. Actually, let's make it a little more simple. Let's do x minus 1 times x plus 2. Okay. Now I'm writing this. I'm not actually graphing it. Now what I'd like, what I'd like you to do is real quick, just say in private chat, what do you think the equilibrium solutions are? It's going to be x equals something and, spoiler alert, x equals something else. So if you would just say in private chat what you think the two equilibrium solutions are. Okay, good. For those of you who put something in chat, thank you very much. I really appreciate the participation. So now, indeed, one of them will be x is equal to negative 2. Another one of them will be x is equal to 1. I move this over so it looks all nice. Now, without actually plotting this, and of course you could go ahead and plot it in the applet, but the bigger deal would be to just say, without plotting it in the applet, how can you say, or what would you say is the the stability of x is equal to negative 2? So hopefully you have not plotted it in the applet. If you have, well, then this exercise doesn't have any value. But if you haven't, just take a guess. And I really don't care right or wrong. In fact, I'm not even claiming it's going to be possible to guess easily. Just take a random intuitive guess. For x is equal to negative 2, do you think it's stable or unstable? Just take a guess from your heart. What do you think? But don't worry too hard about it. It's not about getting it right. It's just about having something to start with. Do you think it's stable or unstable for x is equal to negative 2? Okay. I'm seeing, so for those of you who put something in private chat, thank you. I'm seeing, I think the majority saying unstable, but there's a good chunk for each. Let's just suppose we say, let's say we say stable, whatever. And this is going to be my guess. It's just a random guess. I don't even know offhand because I haven't thought about it that hard. So now if we go and we look, let's now check it, see what we actually get. If we take x minus 1 times x plus 2, we update the graphs, and then we look when x is equal to negative 2, we see, oh, it is stable, okay. But the bigger question is, well, how can we predict for sure? Like, I just took a shot in the dark. I asked you all to just take a shot in the dark as well and just guess. But now what we want to do is we want to try to make a conjecture how we can do no matter what. And what we have to work with, make a conjecture that we can guess it correctly no matter what. And what we have to work with is this, where we actually have a graph. Down here, notice that we didn't have a graph, but I claim that you will have a graph here. So the two equilibrium solutions are negative 2, and we can see that that gives stable. And then there's this one, which is x is equal to 1, that gives unstable. You can see how the solution curves get either pushed away or pulled in towards. Now with that, I claim there's a nice way to just look at this graph, and once you recognize that it's actually relatively straightforward to way to see how it works. But you can just look at this point, look at how the graph acts around that point, and then make the claim from there. So what you want to do right now is just take a minute or two and make a conjecture. And while you're doing that, I'm going to re-type the similar steps to what we went through before. So the first thing we did was investigate behavior. Now the thing that you're doing is make a conjecture on how to determine from the left graph whether an equilibrium solution is stable or unstable, or the best one would be if it included semi-stable. Yeah, feel free to send me your conjecture and I will try to respond. All right, I'm going to chime in here. So I had 2 conjectures that I was able to respond to, and then a bunch kind of at once that I won't be able to respond to quickly individually. And I'll just say all the ones that I've seen so far, it looks good. I think they'll be correct. The only thing that some of them I've seen so far missing are how to predict whether a equilibrium solution would be semi-stable. So, for instance, if I do this, let's say we look at the function, how about just x squared? There's one equilibrium solution, which is right here. And if we do a bunch of curves, we'll notice that this is a semi-stable solution. Now, since your conjectures looked good to me, or at least the ones that I saw by and large, I don't think it'll be too hard to extend those to the case of semi-stable by keeping in mind what's going on here. So here we have semi-stable. Or if you do something like this, what about x minus 1 to the 4th? And then you look at the point 1, we again notice that there is this semi-stable behavior. Now, either way, what you want to do at this point is, once you have your conjecture, is come up with a few other functions. Like I've done here, I generated x squared and x minus 1 to the 4th, and then just see if your conjecture holds up. If it doesn't, you want to go back and revise it. But if it does, you can move on. That's what you wanted to do, is conjecture something, test it, and then hopefully that conjecture holds up. I'm going to double check that I'm not forgetting anything. No, I don't think I've forgotten anything. So with that, I think that concludes what I wanted to show you today. To view the next video in this series, click the link on the right. To view the last video in this series, click the link on the left. If you want to learn more about me, the nerd who's making these videos, visit the website below. And as always, have a good day.